Hey everyone, thanks for coming by the space. Excited to have everyone here and share a little bit more about what we do, what we work on, and also maybe, hopefully everyone leaves the room with knowing a little bit more about multimodal data and also just data processing in the AI age. So here at Daft, we work on data processing for any data at any scale. It is an open source project. We have a few users in the crowd, so thank you users for all your support. Thanks Andrew, woo, you know. And then, you can install it with pip install Daft if you're a Python user, very easy. Today I'll be talking to you about running models on data when your ETL becomes actually very expensive, right? A little bit about me. I am one of the co-founders at Eventual. Our office is right here downstairs, so welcome to the space. And previously I worked in biotech and self-driving, where I did a lot of distributed infrastructure for data within ML and AI. So let's just jump right into it. All right, big data energy. Right? Let's look at what data was like in the past and what it's like now. So in the past, every company was trying to be a data-driven company, right? In like the 2010s, this was the big hype. The way that you became a data-driven company was that you would invest in big data technologies like Hadoop, Spark, and then more recently maybe things like Trino, right? These are big data technologies that help you go essentially from raw data, which comes in, fairly tabular structured formats, JSON, CSV, what have you. You'll clean that data up, and then it becomes clean data, very nice structured tables. And at the end of it all, you're doing analytics. There's an analyst, right, who looks at these charts and graphs, and you make business decisions and business intelligence decisions off this. In 2025, it has changed a little bit, with the introduction of agents and AI. But the general shape of it is still kind of the same. You have raw data, but now instead of just these JSONs and logs that are coming into your system, additionally there's more unstructured things. Right? You might be working with JPEGs, you might be working with PDFs, HTML, emails that come in, maybe Slack threads, right, that are coming in, Zoom recordings, audio calls. And you're still doing this processing to get it into a more structured, searchable format. But the interesting thing is that, you're actually running a lot of LLMs in the loop. And once you have that, it's not analytics anymore. Now everyone's trying to run these agents on them, right? Which are slightly different. Instead of just plotting charts and graphs, a lot of the time you're retrieving the appropriate context and then running LLMs in the loop, in an agentic loop, to do certain tasks. So interestingly, I would argue that if you squint, they look very similar, right? You still have the raw data into process form into some sort of use case. The main use cases are, number one, your raw data now tends to be unstructured and multimodal, big change. Number two, because of that, a corollary is that now you actually need things like LLMs and VLMs, visual models, right, to process that data. Now it becomes very important for you to run these extremely computationally intensive models and workloads in order to get that data into that structured format. Number three, and this was a little bit subtle, people often call Daft a query engine, and I tend to say that it's more of just a general data engine because retrieval now is very important. It's not just querying the data and using SQL to compile these reports. You're often just retrieving the data and then feeding that to the LLMs and the agents, right? Because what do LLMs love? They love context. They love relevant context, and so feed it as much as possible. And then lastly, the interesting bit is that agents are now users too, and so that has led to the rise of, say, MCP servers and that kind of stuff. And so it's both agents and humans that are using these sort of systems now. So here are some assertions that I'm going to make, which I think are true. LLMs are smart enough, or they will be soon, right, for these agentic workloads, and therefore context is going to be king. If you want your system to work really, really well, give it good context, right? And at the end of the day, actually, if you think about it, context is just data. It's just being able to get the right data, get the process data so that it gets there in the first place, and then being able to feed that data then to the LLMs in a timely fashion. And so my overall sentiment here is that, hey, I think we just need better data systems that can do AI, right? And that's essentially what we do at Daft and Eventual. So this is the overall picture where you have raw data coming in at the bottom. It's things like Parquet and JPEG and JSON, MP4, and then now you have the data pipelines that bring it all into more specialized databases, right? People often start with something like Postgres, great first choice, but then once you get to more specialized use cases, you might start thinking of things like full text search, right? Elasticsearch. You might start thinking about data warehouses for analytics, right? Turns out all of them still need to do queries and analysis. You obviously have vector DBs, which I don't have in that picture, because so much of it has been subsumed by a lot of these other specialized databases. And of course, you have file storage, such as AWS S3. But now that your data has been pre-processed into these specialized stores, now it's useful for the humans who want to analyze the data, for the AI agents who want to slurp it all up and find the appropriate context in order to do their work, right? So there's this like dynamic context retrieval and querying that happens in the context store. But what's important is that you kind of need this data pipeline layer, which hasn't been built that well until Daft, right? For data that lands in there, such as your Zoom calls, your Slack threads, your marketing videos, user-generated content. That's a huge pain, right? There's all these like kids who are uploading all kinds of, who knows what's on those images. Snowflake SQL queries, right? If you have a whole bunch of SQL queries landing into a bucket, you want to be able to run analysis over it. Or like a meetup presentation. I might want to throw in meetup presentations and have my agents give me better ones. And so yeah, why is processing this data hard then? Because it requires you to run a lot of models on multimodal data. So let's run through a little exercise. Who in the room has used Spark before? Okay, who loves Spark? Oh wow, great. So let's build a pipeline in Spark. First of all, we're gonna download data. Imagine you have 1 million URLs, right? You're gonna decode this data as JPEG images. And then now we're gonna convert them to tensors, run them on a model, embedding something, right? We'll run a model that requires a GPU. What does that code look like today? First thing you do in Spark, you repartition the data. You're like, a partition? Why do I have to think about a partition? This is why. Back in the good old days for tabular workloads, your data tends to get smaller over time, right? Because you in the process of analysis, you're actually doing a lot of grouping operations and aggregations, summing up the data, counting the data, doing things like mean and max, right? So the data gets smaller over time, and at some point it becomes so small that you can just chart a graph, right? And you're done. That's the end workload. For multimodal data, it's very different because you're doing things like, imagine you have a terabyte of URLs. You're then converting those URLs into images. Big inflation, right? And then it's JPEG, and then now you're converting it, you're decoding the images, which is a further 20x inflation, approximately for JPEG. And then you're, say, running a model, which requires GPU memory. So these multimodal AI workloads tend to inflate and deflate quite a bit, and it's very unpredictable. And therefore, the user has to care a lot about how big your kind of shards of data, partitions of data are. And when you use a system like Spark, oftentimes it goes out of memory. And then you have to be very cognizant about, okay, exactly how many shards are there in my system? How many machines do I have? And there's a huge kind of cognitive overhead in terms of like things that you have to think about. Second thing you're going to do, you're going to run a bunch of Python functions in Spark, which is a JVM engine. So yeah, you will write your own downloading function in Python, and you would write your own image decoding function in Python and try to install all the libraries in Spark and try to get that to work, right? Huge pain. And why is this the new norm? Actually, I had a comment today from some of our partners in China at ByteDance, and they were like, hey, actually, when our users use Daft, all they do is UDFs. It's just UDFs all the way. It's Python functions that users provide us, right? And in the traditional tabular world, most databases provide you with the functionality. They give you the way, the arithmetic to add numbers together. They give you a way to calculate the mean or the hash. However, in multimodal AI workloads, the data by definition is almost like user provided, and therefore the functionality also has to be user provided, right? It's impossible for me to kind of predict all the possible things that a user might want to do on their data, because there might be a new CV algorithm, a new ML model that a user might want to run. And so this almost becomes a first-class citizen. And I like to describe it, interestingly, as that looks a lot less like a database and more like a web app, because web apps are responsible for running user code and not dying and failing when the user code like fails, right? We give you like a little nice error code instead of crashing the entire thing. But most traditional SQL engines are just built to like end-to-end, doesn't fail, runs everything end-to-end. All right, last thing. Now you're running a model, and now you gotta use some GPUs, you gotta use OpenAI, something, right? And you try to run that in Spark, and it's a big pain. Again, in tabular workloads, you don't really do these things, but now in the new world of multimodal AI, this is a very common workload. Call OpenAI 1 million times for each row, right? And that's extremely expensive, and if it fails halfway, like sorry, your 900,000th call and everything else before is kind of wasted, right? It's extremely expensive. Every operation you do now is actually expensive. You might be using GPUs, and Spark is notoriously painful to configure to run over your own GPUs. And so, yeah, unfortunately, these systems just don't work that well. Now, with Daft, let's do some quick demos. This is going to run all just on my local machine, just for simplicity. But it's also very easy to scale this in a cluster in the distributed setting. But let's see what Daft just kind of looks like through a demo. So Daft is a data frame. So I can read this Delta Lake table, which if you're not familiar, it's just a table format. And so now I can look at the data. It looks like this, which is a little messy, which is why I had to prune the columns. There we go. So it's just a table of data. This is ImageNet. So it has folder, file name, source from this database, size, and actually, interestingly, a bunch of bounding box objects. Now, I'm going to prune this table a little bit because it's a little bit unwieldy, hard to view in the demo. So I'm just going to grab the folder and file name column. Here's the first 3 rows, a lot cleaner now. And I'm going to now convert the folder and file name into URLs, right? So here are the first 3 URLs of, I've stored the data in S3, and this is the URL. It's in our Daft public dataset bucket. And so now it's just a table of URLs pointing out to these JPEG files. And to go from URLs down to images, you just do say, hey Daft, take the URL column, download those URLs as bytes. You declare that. And then now you declare, now take those bytes and decode them as images, right? And in about 3 lines of code, you've gone from just tables to images. And Daft does this under the hood, all in kind of very highly performant async Rust code. And now we have also started baking in a lot of really powerful functionality with working with these complex types like text and images. For example, embedding images now is as simple as importing a little embed image function from Daft. And we just run a default, I believe in this case, transformer algorithm. It's running on my local machine. And yeah, you get embeddings. And you've just kind of done what all the steps you need to do to get your data into, say, a vector DB, right, in about 4 lines of code. And this runs extremely efficiently. You can kind of pipe it to a cluster, run this distributed. This embed image actually, I think, supports other providers as well. So you can say kind of like provider equals, OpenAI, and then get it to work on like kind of an external provider. We are, of course, working on a commercial offering as well. And so at some point, eventually you'll be able to say eventual, no pun intended. But yeah, and have this kind of work with more kind of optimized variants of this, right? And run this even with even higher throughput and efficiency. And lastly, I think the developers in the crowd are like, I just want PyTorch, just give me PyTorch, right? So this is what that looks like. You can convert Daft data frame to a PyTorch dataset, and then now this is a format that your models will slurp up, right? So Daft is going to do a lot of batching and getting all the data ready for you and buffering, and then now you have just numbers, a bunch of embeddings and tensors that your models are ready to just slurp up, and it's super fast because we do all this like streaming execution and pipelining under the hood. So yeah, that's kind of what we've been building with Daft. All right. Why is this so interesting? We've been building Daft now for 3 years, and really over the 3 years I've been building it better and better for specifically these use cases. First of all, what we do is something we call dynamic streaming execution. Basically, in processing, most of these engines kind of very naively take big partitions of data because turns out you kind of want to process 128,000 integers all at once. Doing that with video and images is a really stupid idea, like crazy idea, right? So what we do is we actually detect what a user is trying to do and dynamically size these batches so that you get the best of both worlds of parallelism for something like URL downloads, but also the pipelining effect that you need in order to maximize all the resources on your machine without going out of memory. And so actually we started doing this by default at the start of this year, and we've seen kind of a 10x increase in throughput in many cases because of these batched and pipeline operations without going out of memory. And the second thing we're doing now is this idea of first-class support for model providers. So kind of what you saw with that embed image functionality, we're going to have the engine work natively with these model actors that we can spin up on the fly and scale up and down, and we understand how much data is making it through the engine and kind of also control the auto-scaling of those models. And so we give you basically peak efficiency over your entire data pipeline. Oh, I guess one thing to be said here too is if you've ever ran like a pipeline and tried to hit OpenAI or Claude and it's giving you a rate limit error, that's really painful. There's like 429, slow down, right? And that's something that data engines should be responsible for. We should be aware that your endpoint has, I don't know, like a 5,000 requests per second limit and be able to respect all of that. And lastly, yeah, we've been baking in a lot of native support for these complex types of operations. You all saw already the URL downloads, image decodes, and Daft runs this all natively under the hood without the user having to define extremely inefficient Python functions to do this. And yeah, that's it. Thank you. We are hiring, so if you're interested in databases, data systems, these like large-scale, petabyte-scale operations, we are hiring for folks on the core engine to work on open source. Also for the product, if you're a web front-end, back-end, full-stack programmer, we'd love to chat. And also for AI dev advocacy, yeah, we'd love to chat. That's it. Would love to take any questions.
I'm just trying to make sure I understood where you stand in the overall pipeline. So basically Daft, you retrieve unstructured data from S3, for instance, embed it, and put that in a vector database. That's where you...
Yes, so that's one use case, right? Okay. The overall picture of where we fit in, I think, is best described with this diagram, right? Where a vector DB, I think, is an example of somewhere you would store context and retrieve context from. But in order to get your data there in the first place, you have to do a lot of heavy processing of your data. And so embeddings is one example. Other examples that we've seen, for example, are labeling. That's another big one, right? If you have a lot of images coming in, you kind of want to pre-label a lot of the data coming in with models, maybe humans in the loop, so that once your AI systems, your agents are ready to kind of retrieve that data, it's all pre-labeled. So labeling is another interesting use case. Summarization, and also kind of generation of, like say, captioning of images. That's also another big use case that we've seen. Turns out that our systems today work a lot better with text than they do images. And so one trick is if you're working with images, caption them first and then embed them. Or like literally just store the text, and it is a lot more useful for your systems downstream, like the agents.
Thank you. And the second question is, so you work with text and images. Is there planning to work with videos?
Yeah, great question. That's something we're working on actively right now. One of the coolest developments in Daft, we're going to talk about this, I think, in our contributor sync maybe next week, is the addition of a file type, like just a generic file. And the way that you work with it is that as a user of Daft, you write a Python function and you receive a file type, and you can write whatever operations you want to do on top of it, such as run a video extractor. And then in Daft, what we do is we lazily load that file in and also handle all the I/O and concurrency over the file. So that's how we plan to work with videos, because videos are interesting. They're more of a container format rather than like a specification. Because MP4s inside of it can actually contain an arbitrary number of codecs, and it's a very complicated thing. And so we've kind of just exposed these to our users as files and allow the users to run, say, FMPEG or any other solutions that they already use on those videos. Yep.
Thank you.
Yeah, thank you. Great questions.
What is the philosophy for extending this very efficient primitive that you showed, like I guess that UDF, for lack of a better word?
Yeah. So I think on the model side of things, we want to be able to provide users with like as good of an abstraction as possible. And that's interestingly only become possible maybe within the last year as OpenAI SDK has kind of become the standard across all these models. And so now we can actually provide a very good abstraction because anyone that's OpenAI SDK compatible is now automatically compatible with Daft, kind of like the endpoint style approach of working with models. For other things, we do expose a GPU-based UDF, and so you can specify within your UDF, hey, this UDF requires 1 GPU, and Daft will take care of scheduling that for you. And but a lot of the actual kind of batching and stuff, the user still has to do. We are exploring automatic kind of batching for the users, and so for a user, you might just receive tensors, like GPU CUDA tensors, and just do work on top of it, but that's a little bit still in the works. And then for normal UDFs, yeah, you pass us Python functions and we'll figure out how best to run them. And we have some knobs that you can tweak in terms of concurrency, requesting more resources for certain heavy operations and the such.